Hello everyone, this is Radha Hawk presenting my findings for Physics 2211 Lab 4 on oscillations. The purpose of this lab was to analyze the 2D motion of a mass on a spring which was swinging in an arc while simultaneously oscillating vertically. Using Tracker for video analysis and ClosScript for computational modeling, we compare predicted and observed motion to test our physics model and verify whether the energy principle is satisfied. The system we used is the mass alone, the surroundings are the earth and the spring. Two forces act on the mass, gravity pointing straight down with magnitude mg, the spring force pointing along the spring toward the attachment point with magnitude k times s, where s is the stretched length of the spring. We apply the momentum principle, which states that net force equals mass times acceleration to update velocity and position at each time step. Since both forces are conservative, we also track three forms of energy: kinetic energy, gravitational energy, and spring potential energy. We performed video analysis using the video that was already given, which you can see on the right. Before tracking, we calibrated the length scale by placing a calibration stick from the attachment point down to the center of the mass at static equilibrium, a known distance of 0.7 meter. The origin was set at the attachment point, with x horizontal and y negative downward. The frame rate is 95.24 frames per second, giving dt is equal to 0.0105 seconds between frames. Beginning at frame 22, where motion starts, we click the center of the mass each time to extract x and y position data. And you can see the results that we obtained. At the right, you have the graphs of x and y versus time, which we will be analyzing in more detail now. The x position oscillates between about minus 0.13 and plus 0.17 meters, while the y position oscillates between about minus 0.65 and minus 0.75 meters, around an equilibrium of minus 0.7 meters. To estimate the period from each direction separately, I counted the number of complete oscillations in the data. From the x graph, approximately 3 full cycles occur between time t is equal to 0 and t equal to 4.5 seconds, giving a period of 1.5 seconds. From the y graph, we receive the same. The two estimates are identical, which makes sense. Since the mass is one object moving under the same forces, x and y must share the same period. Now let's discuss how we obtained each system property. The mass of 0.402 kg was provided. To find the spring stiffness k, we used the relationship between the oscillation period and the spring constant. Rearranging the spring formula gives k is equal to 4 pi square into m divided by t square, which with t is equal to 1.5 seconds and m is equal to 0.4.2 kg gives k is equal to 7.05 Newton per meter. To find the relaxed length L0, we use the static equilibrium condition. At equilibrium, the spring force exactly balances gravity, meaning k times the stretch equals mg. The equilibrium y position from our data is approximately minus 0.865, so solving gives us L0 is equal to 0.301 meters. The initial conditions for the computational model were derived directly from our tracker data. The initial position was taken from the very first row of data, where x is equal to minus 0.126 meter and y is equal to minus 0.815 meter. The initial velocity was calculated from the first two rows of position data divided by time between frames. This gives Vx is equal to 0.333 meters per second and Vy is equal to minus 0.295 meters per second. Do note that the initial velocity is not zero. The mass was already in motion when tracking began. Using the correct initial velocity is critical for the model to match experiment from the very start. And at the right, you can see some of the rows from the CSV file which we used. Here is the core of the ClosScript computational model. At each time step, we first compute the spring vector L, the vector pointing from the attachment point to the ball's current position. From this, we get the unit vector L hat and the stretch S. We update the energies using the formulas already shown in the slide titled Physics Principles Used. We then calculate the gravitational force straight downward and the spring force pointing back along the spring toward the attachment point. Adding this gives the net force. We then apply the Euler method, applying the net force by the time step and divide by mass to get the change in velocity, then multiply velocity by the time step to get the change in position. The time step is 1/210 seconds, which is about 315 times smaller than the oscillation period, ensuring accurate numerical integration. Let's get into results. This graph compares the x position predicted by our model in blue versus the actual experimental data from the tracker in red. The agreement is very good. Both curves have the same amplitude of about 0.15 meter and the same period of 1.5 seconds. A small phase shift develops over time, meaning the model gradually gets slightly ahead or behind the experiment. This is expected because our model assumes a perfect frictionless system, while the real system loses a tiny amount of energy to air resistance and friction at the attachment point. Overall, the x direction comparison strongly supports our model. The y position comparison also shows good agreement between model and experiment. Both oscillate between about minus 0.78 and minus 0.94 meters with the same period. The y amplitude is noticeably smaller than the x amplitude. This makes physical sense because vertical motion is constrained by both gravity pulling down and the spring pulling towards equilibrium, while horizontal motion is only driven by the horizontal component of the spring force. Again, a small phase shift appears over time for the same reasons as an x. The overall match confirms that our model correctly captures the 2D dynamics of the system. This is the energy analysis of the graph, which is very crucial for verifying our model. The blue curve shows the change in kinetic energy, the red curve shows the change in gravitational potential energy, and the green curve shows the change in spring potential energy. All three oscillate as energies continuously exchange between these three forms. When the mass speeds up, kinetic energy increases while potential energy decreases, and vice versa. Most importantly, the orange curve shows the change in total energy remains essentially flat at zero for the entire 5.5 second simulation. This means the total mechanical energy is conserved, confirming that the energy principle is satisfied in our model. The tiny deviations from zero are due to the finite time step in the numerical integration, not a physical error. The lab tasks us to estimate the oscillation period separately from x and y data and compare them. From the x position tracker graph, I counted approximately 3 complete oscillations between time t is equal to 0 and t equal to 4.5 seconds, which gave tx is equal to 1.5 seconds. And I got the same for ty. The two estimates are identical. This is physically expected. The x and y motions are not independent. They are both driven by the same spring force, which is a single vector that couples both directions. Therefore, both directions must oscillate at the same natural frequency, which is determined by the spring stiffness and the mass. Now, here's further in-depth about the sources of error and assumptions, which I already went over during the discussions, but here is just an in-depth explanation if you want to have a look. In conclusion, this lab successfully demonstrated that the motion of a 2D spring mass system can be understood and predicted using fundamental physics principles. Our closed-grip computational model, built using Newton's second law with gravitational and spring forces, produced position predictions in both x and y that closely matched the experimental trigger data in amplitude and period. The energy analysis confirmed that total mechanical energy is conserved throughout the simulation, validating the energy principle. The period of oscillation was consistently estimated at 1.5 seconds from both x and y data independently. Small discrepancies between the model and experiment are attributed to real-world effects like air resistance and friction that our ideal model does not account for. Overall, this lab reinforces that even complex 2D motion can be broken down and modeled accurately using the same physics tools we've developed throughout the course.